Alright, so we're going to do the derivatives of trig functions. Okay, I don't know when they started figuring these things out, but it is really cool the fact that you could draw all these tangent lines on a graph like this, and you plot the points, and it just happens to be another nice function. Like, this really is fast. Because you could almost imagine if I did all of these, it should just come out to be something wonky and weird. But the fact that it comes out to be another nice function. So let's look here. You see I've got my sine graph. I'm starting right at 0. Looks like I've got a perfectly 45-degree line with a slope of 1. And sure enough, I've got my derivative plotted at 1. Now what's going to happen as I go up to pi over 2? Can you see at pi over 2 that our tangent's going to be completely flat? So if I drag it right up to there, sure enough, it's completely flat. I'm going to drag it a little slower in between that section. And now can you see now that my derivatives are all negative? So in my graph here, my slope of that line is negative. Everywhere from here to here, my derivative graph is below the x-axis, because my tangent line will always be sloping down from left to right, and then until it hits here where it's 0 again, and now it slopes back up. What graph does that make? What does that look like? Cosine graph. Another sine graph. A sine graph with a shift. Yes, it would be correct if you wrote it as a sine graph with a shift, but we are just going to write it as cos of x. What do I have here? Cosine. So here's our cosine graph. Now one of the things that is going to be, well, we'll look at the cosine graph first. Can you see that immediately once I start moving to the right, which way is my tangent going to go? Will it be a positive slope or a negative slope as I'm moving to my right? It's going to be negative. So it makes sense that our derivative line starts going down like that. It stays negative until we get to pi where it's 0 again. And then from pi to 2 pi, those slopes are positive. Now, of the infinitely many different sine and cosine graphs that you could describe this as, which one do you think is the easiest? Negative sine. So derivative of cos is negative sine. Now, the fact that the derivative of sine is cos and the derivative of cos is negative sine, and later when we integrate, we'll go backwards with that, the negative here can cause people difficulties, because it's easy to forget which one's negative and which one's positive. Okay? The best way I've found to think about that is go back to your graph. Think of either one. Here's my sine graph. If I start going to the right with my sine graph, or even when I start, if I draw my tangent right at 0, does it have a positive slope or a negative slope? It has a positive slope. So the derivative of sine is going to be a positive cos. But when I look at my cosine graph, I'm starting right at 0. As soon as I move to the right, my tangent line is negative. So I know that immediately those values are going to be negative, and so the derivative of cos is going to be negative sine. So that's one thing, one way that I help remember that, it helps me remember that. To come up with something that helps you remember that. Now the last one. What's going to happen with tangent? Okay, that looks pretty. If we keep going, can you see that the slopes of the tangents on tangents the slope of tangent on tangent, you see that they'll always be positive. That red line never has a negative slope. What kind of graph does that remind you of? Cotangent has the same curve as tan, just backwards, but you're close. It's one of the reciprocal ones. Okay, it's like an absolute value of secant. Okay, because secant, if you think of your cos graph, I don't know if I can draw in here. Nope, doesn't let me draw in here. But your cos graph would have a maximum right here at 0, 1, and so the reciprocal of cosine is secant. Seems to match up with that. And so thinking of the absolute value of secant, because that would flip them up, is a good guess for this. Okay? What would be another thing that could flip all of your negative values up? Because it's not the absolute value. You guys are close. You've got secant. It's got to do something with secant. But what would be another way of taking all your negative values and making them positive? Squaring it. Yeah. And the derivative of tangent is secant squared, which you could write as 1 over cos squared if you would like. So try those 3 examples underneath, and example 2 with the equation of the tangent. Here they are, the first 2. How did you do? Derivative of sine is cos, so f prime of x equals 4 cos x. Again, that constant value in front, just like it didn't affect anything with the power rule, doesn't affect anything with sine and cos. So this negative 1/3 in front of cos won't affect the derivative. What's the derivative of cos? Negative sine, so it becomes positive 1/3 sine x. Derivative of tan becomes secant squared x. And then the derivative here, 9x squared. So when we start doing the derivatives of sine and cos and tan, as well as the derivative of the natural log of x that we did the other day, this is where things get a little bit more complicated, and you got to take a breath, because I had tan and now it's secant squared. It looks quite different. Whereas when we were doing the derivative of 3x cubed, you could say, oh, I can still see the original function in here because it's just subtract 1 and the number came in front. You feel like those are tied closer together, nicer. But going from tan to secant squared feels a little bit like a stretch. Okay. Now, numbers in front don't affect things, but numbers inside of a function do affect things. We haven't learned how to deal with those yet, but all we can do in this one is look at this and say, Also, we have rules for just sine, just cos. We don't have any rules for dividing. We have rules when we added and subtracted 2 functions. We could do them separately, like we did in B. But we haven't learned the rule yet for dividing, and it's not as simple as doing the derivative of the top over the derivative of the bottom. So one of the things that is very helpful in derivatives, and in everything you're going to do in calculus, is have strong algebra skills. Is there something I can do to this equation to simplify it, to change it into a form so that doing the derivative will be easier? Sine 2 theta was one of your identities. What's it equal to? 2 sine theta cos theta. Why is that helpful? Because your sine thetas disappear. Just becomes 2 cos theta. The derivative of cos theta is negative sine theta. So the derivative of sine 2 theta over sine theta becomes negative 2 sine theta. Find the equation to y equals sine of x. Here's our graph of sine of x at the origin. There's our tangent line. What do we need? We need a slope and a point. We have a point already, 0, 0. Our derivative of sine is cos at x equals 0, and you're going to need to know your pi plate or your unit circle values. What is cos of 0? 1. So now we know our slope is 1. And since the origin is our y-intercept, we can write it in y equals mx plus b form right away. And our tangent line is just y equals x. And this is a good example of an easy-looking answer that, I don't know, sometimes those easy-looking answers make you feel wrong. It's like, oh, that was too easy. I must have done something wrong, so I will erase all the good work I did, make up bad math, and lose all the marks I possibly can. Yes, good strategy.